Okay, so it's a real pleasure to reintroduce Professor Óscar Domínguez from the University of CUNEF from Madrid. Since the last time I introduced him to this seminar, he won a contract with the Ramón y Cajal, very prestigious contract to do research for 5 years. He solved an open problem that was in the theory of fluids that was open since last century. He published many papers and monographs. So this is just 1 year from the last time that I introduced him. So it's a pleasure to have him again here. So Óscar, please go ahead.
Thank you very much. So first of all, I would like to thank the organizers of this Mischa Cotlar seminar for giving me the opportunity to talk again in front of this distinguished audience, and especially my thanks go to Mario Milman. Okay, I'm very happy to collaborate with him, and I hope that this will continue for many years. As Mario mentioned, my talk can be considered as an updated version of the talk that I gave in the same seminar around 1 year ago. But now I think that the picture is it's better understood. So the topic will be on the DiPerna-Majda gap problem for 2D Euler equations. And this is based on joint work with Mario Milman and Daniel Spector. So let's start with the talk. All right, so I will try to make a very accessible talk for a wide audience and to make it self-contained. I will start from the very scratch. So let me introduce the main characters of this talk, namely Euler equations. Okay, so consider the flow generated by an ideal incompressible fluid. And this flow is covered by the so-called Euler equations. So these equations were already formulated in the 18th century, but there are still many challenging and interesting open questions related to Euler equations. In this talk, we are only interested in the R2 setting. So all function spaces defined in this talk are defined on the whole plane, on the full plane R2. And here you can see Euler system. So this equation, okay? Note that this is a system of two equations because U is a vector field. So it has two components, say first component and second component. This equation may be considered as a formulation of the second Newton law with internal force given by the right-hand side minus the grad of P, and P denotes the pressure, and this is a scalar. Okay, so here the unknowns are U, the velocity field, so two components, and P, the pressure. So we need to add one more equation to solve the system, namely the second equation given here, divergence-free assumption on U. So from a physical point of view, this means that the fluid is incompressible. That is, if the fluid is expanded through the, say, x direction, then it should be compressed into the y direction to compensate. And we also have the initial condition. So the fluid at the initial time 0 has the prescribed value U0. Okay, this is a function defined on R2, taking values into R2. This system has many challenging features. In particular, it is a non-linear PDE. So here one can see the non-linear term, U times grad U. In addition, it is a non-local system. Indeed, one can recover the pressure from the velocity via this Laplace equation. So the Laplace of P is equal to this expression depending on the velocity field. Or in other words, one can recover P from U via the action of the inverse Laplacian. And this is a non-local operator. Okay, so here to get P from U, one has to add a non-local operator. In other words, what is happening close to the origin is also affected by what happens with the fluid very far away from the origin. Okay, so this is a challenging feature of this equation. And know that this relation between P and the velocity field is a simple consequence of taking the divergence on both sides of this equation and using the incompressibility condition on U to remove this first term. It is well known that in the study of Euler equations, the following quantity plays a central role, namely the vorticity. It's denoted by omega, and this can be defined as the pure of the velocity. And in the 2D setting, this expression admits the following nice characterization. The following nice can be described in terms of this nice expression involves the partial derivatives of the velocity field. All right, so this is a scalar. And then most of the results will be formulated in terms of the vorticity rather than the velocity. But this is like there exists a symbiosis between vorticity and velocity because one can also recover the velocity from the vorticity via the so-called Savart law. Okay, but we do not go into further details. Now, the basic question is, can we guarantee the existence of weak solutions of Euler equations? And if yes, how can we construct these solutions? Okay. The answer to both questions are well known, and this was developed in a series of influential papers by DiPerna and Majda in the late 80s. So here you can see these three references, and these papers are highly cited in the area. And in these papers, the authors, motivated by approximations arising in numerics and also working with the asymptotic analysis of Euler equations, they developed the celebrated method of approximate solutions to Euler equations. Some basic examples of approximate solutions can be obtained like the vanishing viscosity limits of the Navier-Stokes equations. That is, here we add a stretching term depending on the viscosity, and then we study the limit as the viscosity goes to zero. And if everything goes smoothly, ideally, this the solutions of the Navier-Stokes solutions should recover the solution of the Euler system. Okay, this is not so easy, but this is what is the idea behind. And one can also construct approximating solutions via smoothing the initial data for exact solutions of the Euler equations. But one can also implement numerical methods such as vortex block approximations, discrete methods, many methods. All right. Okay. And in particular, DiPerna and Majda were mainly interested in the so-called vortex seed problem. This means that the initial data, okay, is a prescribed measure. All right? And in addition, they assume that the measure belongs to H-1 at least locally. H-1 denotes the dual of the Sobolev space H1, all right? And this condition is rather natural because it can be interpreted in terms of the velocity, saying that the velocity belongs to L2. And this means that we are dealing with finite energy solutions. Or in other words, we need a certain decay of the solutions at infinity, because we are working with the full plane. We need that these solutions decay when you are far away from the origin. Okay, so this is the so-called vortexity problem. So initial vorticity are measures in h-1, and this setting is of special interest in applications because, for instance, imagine that you have as initial data, the initial data is supported on a curve. All right, so this is the natural framework to work in this physical problem. All right, so then DiPerna and Majda propose the following definition of approximate solution family of Euler equations. So we will say that a one-parameter family of vector fields, say U epsilon, where epsilon is positive, is an approximate solution if the following three properties are satisfied. So the first property says that you are working with finite energy solutions, approximate solutions. The second condition is the so-called compatibility condition. So this is related to the variational formulation of Euler of this first equation. Indeed, if we multiply on both sides of this equation by a test function, and then we integrate by parts, we will arrive at the variational formulation of the Euler equation. But instead of requiring that this quantity is equal to 0, the DiPerna and Majda studied these approximations. So instead of these quantities going to 0, they only assume that these quantities converge to 0 as epsilon goes to 0. So in some sense, this U epsilon approximates the weak solution, and there is a remainder there. Okay? And of course, one has to add the incompressibility condition, in this case in the distributional sense, for every U epsilon. All right, so as we said, know that this notion, approximate solutions, generalizes the classical notion of weak solution. If U is a weak solution, letting U epsilon to be equals U for every epsilon, then one construct a trivial example of approximate solutions. In this case, these quantities are equal to 0 for every epsilon. All right? But this concept is more real. And now let's see how DiPerna and Majda are able to establish existence of Euler solutions from approximate families. By assumption, this family, U epsilon, is uniformly bounded in L2. And we know from basic courses in functional analysis that working with Hilbert spaces, if we have a bounded sequence, we can subtract a subsequence that converges weakly in the Hilbert space. And indeed, from this bounded sequence in L2, modulo passing to a subsequence, we obtain weak convergence to, say, U in L2. And now the question is, can we guarantee that this weak limit U is indeed a weak solution to the Euler equation? So the point is to be able to pass to the limit as epsilon goes to 0 in this formulation. If we are able to replace here U epsilon by U, we succeed, right? So now, how can we pass to the limit? Here, in this first integral, in this first term, no problem, because we have weak convergence. The same happens here, but this guy is more complicated because there are quadratic non-linear terms. So how can we pass to the limit in this tensor product, right? And now, two possible scenarios arise. Firstly, assume that one is able to update the weak convergence to a strong convergence. If this is possible, then U is a weak solution to Euler equations. Indeed, in this case, one can pass here to the limit and replacing U epsilon by U using the strong convergence in L2. And then we conclude that U is a weak solution. Furthermore, one can show that in this case, U conserves the kinetic energy, at least for all classical approximation approaches. Okay? This means that the L2 norm of the velocity is preserved for all times. All right? And this is a very important property in fluid mechanics. On the other hand, it may well happen that this scenario, the first scenario, is not working. So this means that one cannot update the weak convergence to a strong convergence in L2. If this is the case, then energy concentrates on sets. And the size of such sets can be measured in terms of the so-called reduced defect method of DiPerna and Majda. So here you see the definition of this function theta defined on all Borel sets in R2, like the error of approximation in the L2 metric of the approximating family with respect to the candidate to be the weak solution. All right. So, and this function is very important in the analysis of convergence issues for approximating families. Indeed, if we consider a Borel set such that this guy is positive, this is equivalent to say that E is a concentration set. Or in other words, wild behavior may happen working with the set E. Right? On the other hand, if this function vanishes on E, then this is equivalent to say that we are able to get a strong convergence of the approximation family to the weak limit, okay, in L2 restricted to this Borel set E. So in this case, we are in a very good scenario, okay? So it's very important to understand the behavior of the reduced effect method. And now, a very interesting phenomenon may happen in this second scenario, the so-called concentration-cancellation phenomenon due to DiPerna and Majda. Let me explain this in more detail. The fact that U epsilon does not converge strongly to U in L2, this fact does not imply that U may be still a weak solution to the Euler equations. Indeed, some subtle cancellations may happen working with these quadratic terms, so that despite the fact that this guy is not it does not converge strongly to U, when you consider this the product, then some cancellations arise, and then eventually one is able to get this weak convergence. And then, working with this weak convergence, we can go to the variational formulation here, and then this is still enough to conclude that U is a weak solution. All right? And this is, as I said, the famous concentration-cancellation phenomenon. So, failure of a strong convergence, but this failure can be compensated by nice cancellation phenomena here, so that in the limit we succeed. And then U is still a weak solution to the Euler equation. At least I would like to mention very briefly that there exist strong connections between the concentration cancellation phenomenon and the so-called anomalous dissipation in Euler equations. So anomalous dissipation means that the energy conservation fails to be true. So this formula here is no longer true. All right? So one can construct wild solutions to Euler equations in such a way that this equality here fails. Okay, and this is the so-called anomalous dissipation. And anomalous dissipation is mainly related to the so-called Onsager conjecture. As I said, I don't wish to go into further details because this is not the goal of my talk, but at least I would like to say that Onsager conjecture says that if you have enough regularity measured in some Hölder space, then you have energy conservation. On the other hand, if you are working with rough smoothness, then crazy phenomena may happen so that this energy concentration fails. Okay, and the Onsager conjecture is now a theorem, and it was proved by Iset, and there is another method by Buckmaster, Delelis, Stekelehidi, Bicol, and both approaches strongly rely on the celebrated method of convex integration introduced by Delelis and Stekelehidi. On the other hand, concerning the positive part of the Onsager conjecture, I mean the energy conservation for enough regularity, there are many results, and here I'm quoting some of these, some papers related to the positive part of the Onsager conjecture. Okay, so overall, concentration cancellation and anomalous dissipation are strongly connected. Next, I would like to show you how one can apply the method of approximate solutions for special function spaces. Let me start with the very basic example. So consider the Lebesgue setting, LP, and assume that P is larger than 1. A famous result by DiPerna and Majda asserts that if the family of vorticities, approximating vorticities, is bounded in LP, in particular, this is the case if the initial vorticity belongs to LP via well-known conservation laws, then we have a strong convergence of the related set of velocities to a weak solution U of Euler equations. And in particular, U conserves the kinetic energy. But note that the LP setting is not adequate to measure vortex shifts, because working with measures, LP is not a good candidate, right? And then, to overcome this obstruction, DiPerna and Majda proposed to work with log-Murray conditions to measure regularity properties of vortex shifts. And here I'm recalling you the definition of Murray space with logarithmic decays. So we will say that the measure omega belongs to this Murray space with exponent alpha, log exponent alpha, if and only if this condition holds true. That is, the total variation of the measure of every pole with center x, radii r, can be uniformly bounded by the log of the radii to the negative power alpha. And this bound should be uniform with respect to x and r, assuming that r is sufficiently small. Say here, capital R is fixed, say 1/2, if you wish. It's not important. Let me also mention that in the original paper by DiPerna and Majda, they call this condition like decay rates of the vorticity maximal function. Okay, but nowadays I think that the language of Murray spaces has become very popular. Okay. Note that all Lebesgue spaces with P larger than 1 are continuously embedded into this Murray space. This is a simple consequence of Hölder inequality. Okay, so here we, working with these spaces, we can cover all Lebesgue spaces LP, okay, if P is strictly larger than 1. This is not true if P is equal to 1. Okay. And then DiPerna and Majda obtained the following remarkable result about log lack of concentrations under more regularity with alpha strictly larger than 1. To be more precise, if the family of vorticities is bounded under this more regularity, then the related set of velocities converges strongly in L2 to U, a weak solution to the Euler equations. Okay? And furthermore, U preserves the kinetic energy. And the original proof of DiPerna and Majda relies on elliptic regularity of elliptic properties, regularity theory for elliptic PDEs, and to be more precise, they obtain a nice Helder-type inequality involving the so-called extreme functions. We do not go into further details. Nowadays, there are many different methods different approaches, alternative approaches to the DiPerna and Majda theorem. And in particular, in this talk, I will review some of them. On the other hand, working with alpha equals to 1/2, a celebrated result by Delort in 1991 asserts the concentration-cancellation phenomenon. So here you can read the precise statement, and let me mention that the original formulation of Delort does not involve concentration-cancellation phenomenon. More precisely, Delort shows the existence of solutions in the negative Sobolev space H-1. On the other hand, there is an alternative, and I will say easier proof of the Delort result due to Majda 2 years later, 1993, showing that the Delort result is a consequence of the concentration-cancellation phenomenon under this more irregularity. Okay, so the alternative approach due to Majda established concentration-cancellation for more irregularity 1/2, and in particular, this implies the Delort statement. So here, one can see that there is a gap between this positive result. I mean, if alpha is larger than 1, lack of concentration, so energy conservation. On the other hand, working with alpha equals 1/2, concentration cancellation. And then the DiPerna-Majda gap problem asks what happens in the remaining range. That is, lack of concentration versus concentration cancellation under more irregularity with alpha between 1/2 and 1. So what's happening here? So can we update the DiPerna-Majda result going down 1 alpha from 1 to 1/2, or maybe one can update the result, the negative result by Delort going from 1/2 to 1. So what happens in this remaining range? This is the DiPerna-Majda gap problem. And I would like to quote one of the standard references in the field, namely the monograph by Magda Bertocci. The authors wrote the following. In fact, the discrepancy between a strong and weak convergence is very small. We saw that a slightly weaker decay rate than more irregularity alpha with alpha larger than 1, namely alpha equals to 1/2, allows concentration to occur. However, and this is important in red color, in the case of positive sign vorticity, we can show that this weaker decay rate is the worst that can happen. So this last statement suggests that working with positive sign vorticities, 1/2 is the optimal regularity to achieve concentration cancellation. Okay. However, from a physical point of view, to restrict our attention to positive sign vorticities, it's too restrictive indeed. So because positive sign vorticities means that vorticities measures how the fluid rotates, right? And if the vorticity has positive sign, this means that we rotate only one direction, okay? For instance, forward. But in practice, this is not happening. In practice, you go forward and then backward, forward, okay? So you may have different behavior of the fluid, right? So to restrict attention to positive sign is too much. So what happens in general? So and then to solve the general question, a remarkable effort was done in a very nice paper by Lopez Filo, Nussenbey-Lopez, and Tadmor around 24 years ago. The authors introduced the so-called H-1 stability. So, and this can be formulated in a very general setting of compact embeddings of general Banach function spaces followed by measures into H-1. So the authors saw that a sufficient condition to guarantee the lack of concentration is to get that your space X, where vorticities lie, is compactly embedded into H-1. Once you have this compactness assertion, you gain, and then no concentration happens in X. All right? Okay. It is more or less clear that this result is, holds. Why? Because assume that you consider a bounded family of vorticities in X. So since this embedding is compact, so then you can subtract a subsequence converting strongly into H-1, okay? But this is in terms of the vorticities, all right? But as I told you, there is a symbiosis between vorticity and velocity via the Biot-Savart law, and then working this compactness, one can go from the strong convergence in H-1 of vorticities to a strong convergence in L2 of the velocities. All right? But this is very easy to state, but not so easy to prove, because the path seen from vorticity to velocity via the so-called Biot-Savart law involves the action of non-local operators. Okay, so to overcome this obstruction, the authors of this paper developed a time-dependent version of the famous deep Q lemma, and they are able to achieve this result. All right? As an application of this very general framework, Lopez Filo, Nussenbey-Lopez, and Tadmor can recover the known results by DiPerna and Majda in a simple way. So, because LP is compactly embedded into H-1 if P is larger than 1, recall that we are working with the 2D setting. This is nothing else that the dual statement of the Rayleigh-Kondratiev theorem. And working now with Morley regularity, one can show that this Morley space is compactly embedded into H-1, provided that alpha is strictly larger than 1. And in this paper, the authors attribute this result to the Bohr and tau independently. However, here you see, again, the restriction alpha is larger than 1, as in the original paper by DiPerna and Majda. So different methods, but the same restriction. And then the authors, Lopez Filo, Nussenbey-Lopez, and Tadmor, make the following claim. So I'm going to skip this part and let me concentrate in the last statement in red color. The gap alpha between 1/2 and 1 remains open with regard to the question of compact embeddings of Morley space into H-1. So this method is not working below alpha when alpha is less than 1 or equal to 1. All right. But to be more precise, this question makes sense from a functional analysis point of view, but if you are thinking in applications to the PDE, to Euler equations, it's even more complicated. Because, as we said, the compactness of x into x minus 1 is only a sufficient condition to ensure lack of concentration in x. But this is not necessary condition. So this result here is not if and only if. Indeed, there is a very nice result by Lyons, 96, showing an example of a space, namely the Lorentz space L12, defined in terms of the maximal function related to the non-inclusion rearrangement. We do not go into further details, okay? Such that, but it is well known that this space is the optimal Lorentz, is the optimal rearrangement invariant space, in fact, the optimal rearrangement invariant space that is embedded into H minus 1. However, this embedding, going from Lorentz to H minus 1, fails to be compact. Despite this fact, Lyons is able to show the lack of concentration in L12. So this shows that this result is not a characterization. It's only one direction. And what is hidden here is Lyons is able to achieve the endpoint because we don't need to work with all functions in X. It is enough to restrict our attention to the set of Euler solutions. Okay? So if you consider here X intersection with the set of Euler solutions, then the corresponding embedding is compact. All right. Another interesting approach to the DiPerna-Majda gap problem was proposed by Tadmor in 2001, and to explain his method, let me recall you the definition of packets. So let P be the set of all packets, that is, pairwise disjoint cubes. And it is easy to see that the Morrey seminode can be, the Morrey node can be characterized in terms of cubes. Okay, this is standard. And now a very simple trick using, like, say, Fubini's theorem for L infinity, okay, allows us to rewrite this in terms of the packets, okay? And then Tadmor proposed to replace the inner L infinity node by the little L2 node here. And then he introduced these V spaces, okay, with log regularity alpha. And working with this new scale of regularity spaces, Tadmor is able to achieve the expected threshold, namely alpha is larger than 1/2. So this space is compactly embedded into H-1, and as an application of the H-1 stability method, one can conclude no concentration occurs in V spaces with alpha larger than 1, and in particular, energy conservation holds. However, as mentioned by Tadmor himself, this approach seems not to resolve the gap problem, since he is able to achieve the endpoint 1/2 after refining the Morrey scale to this new scale B. But here, when you go from little L2 to L infinity, right, this space is slightly smaller than the classical Morrey space, okay? So this space is continuously embedded into the Morrey space. So apparently, the Tadmor approach does not resolve the DiPerna-Majda gap problem. There are further attempts to the gap problem. Here, I only mention some of them. So, for instance, this paper using here the authors consider like the 3D version of the DiPerna-Majda gap problem, but working with axis symmetry. So in this case, then there is a certain connection with the 2D setting, at least locally, and then they obtain similar results like DiPerna-Majda, but still they have the same gap, okay, between 1/2 and 1, okay? And in fact, the authors ask what happens when alpha is between 1/2 and 1 in the 3D setting and working with axis symmetry, okay? There are also some very recent papers by Misla, Lantaler, Pares Pulido, also Lantaler, where the authors obtain another approach to the DiPerna-Majda method, but instead of relying of the vorticity, the authors work at the level of the velocities using the so-called structure functions. For people working in function spaces, structure functions are moduli of continuity in L2, okay? But again, they also have the restriction alpha larger than 1 to get no concentrations under model regularity. So far, all these results try to solve the DiPerna-Majda gap problem in the positive direction. That is going from obtaining no concentration from alpha below alpha equals 1. So, and now, today I would like to give you the solution to the DiPerna-Majda gap problem. And this is this result was obtained jointly with Spector, and we obtained the somehow an unexpected phenomenon. So the concentration cancellation under more regularity 1. Okay. So here you can read the precise statement. So we construct an approximation family, and more precisely, an exact study solutions to the 2D Euler equations. They have finite energy. The related set of vorticities is uniformly bounded under the model regularity 1. This family converges weakly to the trivial solution 0, but not strongly. Okay, so and this, in particular, this proves the concentration cancellation under this model regularity. Even better, we are able to characterize concentration sets. I mean, recall that concentration sets are regions where crazy behavior may happen, okay? So we characterize the reduced effect measure, okay? And we say that we obtain that E is a concentration set if and only if this measure mu that I will describe right now is positive. So what is mu? So mu is a certain Forssman measure satisfying this log-decay. And the construction of this measure is given explicitly in the paper. So to be more precise, this measure is the quick limit of these quadratic terms. And these quadratic terms are usually called in the literature weak start defect measure, okay? All right, and note that in general, weak start defect measure may not coincide with the reduced defect measure, but in this particular scenario, they coincide, okay? Both are equal to this Forssman measure with logarithmic decay as R goes to 0. All right. As I told you, there is a connection between concentration cancellation phenomenon and embeddings, compact embeddings between from function spaces formed by measures into H-1. And indeed, this result admits the following formulation in terms of compact embeddings into H-1. So not only this model space is not compactly embedded into H-1, even better, this space intersection with the set of Euler solutions for vortex sheets is not compactly embedded into H-1. And this is what we really need to obtain the concentration cancellation phenomenon, okay? If we forget about this guy, this is still not strong enough to conclude concentration cancellation, okay? Another comment is that our result does not contradict the known fact that 1/2 is the optimal regularity for concentration cancellation when restricted to positive sign vorticities. Okay, the point is that in our construction, the vorticity is mixed sign. Okay, because we know that working with positive signs, this is the best one can get. So to construct a counterexample further beyond 1/2, one has to avoid positive sign, and one needs to come to work with mid signs, and this makes the analysis much more complicated. Okay. Okay, and now in the rest of my talk, I would like to explain you the main ideas behind the proof of this result. Of course, I don't have time to go into further details, but at least I would like to give you what are the main motivations to achieve this result. Okay. Another comment is that here I restrict my attention to alpha equals 1, because this is really the threshold. Once you have this, you have concentration cancellation phenomenon for m log alpha with alpha less than or equal to 1, because locally these spaces are nested. Okay, so 1 is really the endpoint here. So let's see some ideas about the method of proof. I will say that the main new idea underlying the concentration cancellation in m log 1 is sparseness, and more precisely the connection between sparseness and energy conservation. Let me explain you this. So probably most of you are familiar with sparse decompositions and sparse domination, but just in case you are not familiar, let me very briefly recall what is a sparse family of cubes. Okay. Assume that you have a fixed cube, say Q0, where you may assume that Q0 is the support, if you wish, of your fluid, right? Of your vorticities. And let us denote by D the collection of all dyadic subcubes in Q0. And we will say that a family S formed by dyadic cubes is sparse if for every element in the family there exists a measurable subset, say E, such that these two conditions are satisfied. The second condition tells us that the size of E is comparable to the size of the cube Q. All right, 1/2 is not playing any role here. One can replace 1/2 by any fixed constant eta between 0 and 1. Okay? And the first condition tells us that, all right, maybe the cubes Q are not pairwise disjoint, but the related sets are pairwise disjoint. So in other words, sparse families of cubes are not necessarily packings, but the possible overlappings between the elements in the family can be controlled in a sharp fashion. And maybe this definition can be better understood by picture. So here, assume that this is your original cube, Q0, and now consider different dyadic generations. So first generation, second generation, third generation, and so on. And consider the family of yellow cubes. Know that this family is not a packing, right? Because, for instance, this guy here intersects its father, right? This guy. On the other hand, I claim that this family of yellow cubes is sparse. Indeed, for every element in the family, there exists a big portion of it. For instance, in this cube, the upper part, such that this part does not intersect the rest of the measurable sets in the family. Let's go to the second generation. So here, consider this guy on the lower right corner. So there exists a big portion of it, namely this part, and these two guys that not intersect this upper part. Or for instance, consider this guy here. There exists a big part, namely this part here, these two white cubes, such that these guys that not intersect, of course, these two guys, but they don't intersect also the this upper part coming from the yellow cube in the first generation. And in this way, I can iterate the process. Okay. I would like to say that the concept of a sparse family of cubes has emerged as a powerful tool in modern harmonic analysis, since the proof of the well-known A2 theorem by Hitonen, and more precisely, its alternative proof due to Lerner in 2013. I don't wish to explain what is A2 theorem. This is a quantitative version of weighted estimate for Calderon-Sigmund operators with important applications to certain questions arising in PDEs. But this is not the goal of my talk. But there are plenty of papers dealing with sparseness, but mostly they are related to sparse domination principles for many classical operators in harmonic analysis in a variety of function spaces. In this talk, we don't wish to follow this path. We're going to follow a completely different route, and we are going to apply sparse decompositions to get the essence of Euler solutions. So in connection with PDEs and how the geometry played by sparse cubes indeed characterizes energy conservation. Okay? I will explain this in a few seconds, but before that, I would like also say that in some sense, sparse decompositions can be seen as a certain refinement of the classical Calderon-Sigmund decompositions. Okay? This is a way to construct optimal Calderon-Sigmund decompositions. And now here, this is, as I promised, the connection between sparseness and energy conservation. And this was developed in two papers jointly with Mario Milman. To be more precise, this is one project, but we first made an announcement in contradue from the French Academy of Sciences. And in this short note, we only have statements and some applications, but there are no proofs. We spent around 2 years to finish the serious version, and now you can find the serious version, including full details and complete proofs, I think, and also with applications to the Euler equations. Okay, so Mario and I proposed the following idea: H-1 via sparseness. So recall the definition of V spaces as considered by Título. So here we have this L2 node of the total variation of the measures, and no logarithmic regularity is involved. So, and now Mario and I suggested, okay, what happens if we replace here by the set of all packings by the family of all sparse cubes? So then we define sparse V spaces. So here, this test this condition over all sparse family of cubes. And then we introduce sparse V spaces, and we obtain the following nice formula. So sparse V spaces characterizes H-1. And be careful here because, okay, to be more precise, this is not, this means that if you are working with a measure with distinguished sign, then this guy is equivalent to the H-1 node. In general, these two spaces do not coincide, of course, because this is a distributional space and this guy is formed by measures, so nothing to do. But we are saying that we have the equivalence of nodes or semi-nodes working with distinguished measures, okay? And the proof of this result involves sparse domination principles, but now working at the level of function spaces. And indeed, this theorem can be considered as a part of a much more general phenomenon on negative Sobolev spaces and sparseness. So, for the purposes of this talk, it is enough to restrict our attention to H-1, but maybe for another application, one needs to characterize the negative Sobolev seminar in terms of sparse sets, and then one can use potentially use our result. So maybe in the future, one can find further applications of this sparseness in connection with negative Sobolev spaces. And recall that negative Sobolev spaces, even for general P, are very arise naturally in the study of PDEs, right? For instance, working with the P Laplace operator. All right, but now let me focus into H-1, and now let me explain you how Mario and I connected the sparseness with energy conservation. So in a natural way, we introduce sparse indices of a measure, so Sn, and this is nothing else than the remainder terms in this series, okay? We consider here the sum over the sparse cubes with length less than or equal to the 2 minus n. And know that by construction, this sequence is non-increasing, is non-negative, and is bounded by the H-1 seminar. Okay? And a fundamental observation is that the asymptotic behavior of this sequence as n goes to infinity, so how this sequence decays to 0, characterizes energy conservation. So here you can read the precise statement. So consider a family of approximating family of Euler solutions. The related set of vorticities is omega epsilon. So if the sparse indices goes to 0, then you get a strong convergence in L2 to a weak solution to the Euler equations. And in addition, you conserve the kinetic energy. Okay? The first part of this theorem holds true for any approximating family, and for the conservation, for the energy conservation, we restrict our attention to the distinguished example given by Navier-Stokes approximates, okay, vanishing viscosity. Okay, so but this result tells us that in order to understand the energy conservation in Euler solution, it is enough to restrict our attention to the distinguished geometry played by sparse cubes. Forget about the rest. Focus on sparse cubes. This has a very nice geometry, and then let's see what can we create within these sparse cubes. Okay, this is what this result is telling me. Only sparse cubes are important when dealing with energy conservation. And using sparseness, we are able to recover all previously known results in a unifying fashion, because one can introduce in a natural way the so-called sparse indices of function spaces. This is nothing else than the supremum over the related unit ball of all sparse indices. And when dealing with classical function spaces, say LP, Morley, B spaces, we are able to estimate the corresponding sparse indices. So with LP, we obtain exponential decay. With Morley, we have this polynomial decay. And with B, we are able to get a better decay, okay, given by this behavior. Okay? So note that all these guys converge to 0 as n goes to infinity, and then we can use this result in order to recover the DiPerna-Majda result, Lopez-Filo, Nussenbey-Lopez, Tadmor, and also Tadmor in a unifying fashion in terms of sparseness. And not only that, one can also use sparseness in combination with the so-called extrapolation theory of Jauer-Milman in order to construct new optimal regularity classes for energy conservation. But I will skip this part, but just in case that you are interested, you can go to the preprint and have a look. All right. Okay, but note that, again, here, let's focus on this. When working with more regularity, okay, we still need alpha larger than 1. Okay, so we are still not able to solve the DiPerna-Majda curve problem, because we have still the same restriction. But at least for me, this was very useful because the proof of this result, okay, of this upper estimate for the sparse indices is very transparent. It's elementary, I will say. And then there is no too much room for improvement. So this suggested me that maybe, probably, the result was optimal. So, but note that here we have only upper estimate. So it may happen that we were not clever enough to improve this decay. And maybe one can achieve the endpoint one half using another computations, okay? But I was not so optimistic at some point, and then this motivated me with Daniel Spector to construct the decided counterexample for a lack of concentrations under model regularity with alpha equals 1. So so how much time do I have? Do I have 5 minutes?
Yes, of course.
Okay, thank you very much. So in the very last 5 minutes, I would like to explain you in a very elementary way, okay, some ideas in the proof, okay? The proof is technical, it requires some pages, but this is essentially what is here, okay? All right, so this is your domain, say the unit cube to fix ideas. And now inside of this unit cube, we are going to construct a certain Cantor set. So consider here C to be the intersection of all these cubes, all right? So fixed K, for every fixed K, we are considering 4K cubes, okay, with this side length, super exponential decay, okay, of side lengths. This plays an important role in computations, okay? And now the idea is to glue vortex patches. So vortex patch is like a characteristic function. So now we are going to do is the following. So fix the generation K, okay, this generation, okay? And now on every cube of this generation, we are going to glue this vortex patch. So know that, so here what we are doing here is we are considering this ball, and then inside of this ball we describe this value, omega k plus. This is a huge value, very large value. On the other hand, on this annuli, we prescribe a very negative value, omega k minus. And this is done in order to get that the integral of omega k over this cube is 0, so means 0. As a consequence, one can, the related velocity uk still lives inside of this cube. And this is very important, because if we don't have this fact, then even if omega k is supported inside of this cube, it may happen that uk lives outside. And this is due to the non-locality of the Euler equation, okay? But using this construction, we can overcome this. And now we are going to glue this construction on every cube of the family. All right, and now here you can read how can we choose all these parameters so that this works, but one can prove that the total variation at the level k of this vorticity on every of these cubes is exactly the required one. I mean, the logarithmic decay to the power -1. And from here, one can pass to any cube, okay, via a bootstrapping argument, and then showing that omega k is has this model regularity, the decided model regularity. This still is not enough, because now one needs to get the failure of energy conservation, okay, the concentration cancellation. And then to get this, we are going to use sparseness in the following way. All right, so consider this guy, so this cube, or in other words, if you wish, this cube, okay? And now consider the corresponding descendant, for instance, this guy. So let me go here, okay? These guys, okay? Know that this family of cubes is not a packing. Of course, this guy overlaps its ancestor. but they determine a sparse family of cubes, because from here to the original cube, one can construct a dyadic tower of cubes, okay? And know that this dyadic tower gives us a sparse family of cubes. So there are overlappings, but the overlappings can be controlled in a sharp fashion. Once this has been done, it is not hard to compute, to estimate, in fact, the corresponding sparse indices of these vortex patches. So we made some computations. It takes some it's some work, but after some computations, one can observe that this guy is not going to zero, and even much more dramatic, this sequence goes to infinity as k goes to infinity. So this is a wild behavior of the sparse indices. And then one can rely on my joint project with Milman to claim that the energy conservation fails to be true, because in order to get energy conservation, one needs that this guy goes to zero as k goes to infinity. So this is not the case, and then one can use some ideas in my paper with Milman in order to get that the energy conservation fails to be true, and then to finish the proof, okay? Okay, this is the idea of the proof of this result, and I will stop here, and thank you for listening. And